Section 1.3 is going on to more about measurements, specifically the exactness or the approximation of measurements. Accuracy of a measurement depends on the measuring units. We talked about last time, the smaller the units, the greater the accuracy. A millimeter is more accurate than a centimeter, which is more accurate than an inch. And then degree of accuracy can be found by finding the smallest division on the instrument. So if you're looking at a ruler, like for instance on the inches, usually they break them down into 1/8 of an inch. So that's the degree of accuracy for the inches on that ruler. Accurate is if it's close, the closer it is to the exact value. It's almost impossible to find the exact value depending on your measurement tool. There's always going to be some type of rounding. So the upper bound is going to be the exact value of the measurement to the right endpoint. So for instance, if you're saying I'm measuring to the nearest centimeter, then how much of a centimeter can you go up and still be accurate, and how much can you go down your lower bound and still be accurate, given saying I'm rounding to the nearest centimeter or whatever your measurement unit is. So for example, number 1 says Jane's weight is 68 kilograms to the nearest kilogram. Determine the upper and lower bounds of her weight. So if she's 68 kilograms to the nearest kilogram, she's probably not exactly 68.0000 on forever kilograms. So there's this range of weight that she could fit into and still be accurate when I say 68 kilograms to the nearest kilogram. So what is that range of weight? That's what it's asking when it's saying determine the upper and the lower bounds. So basically we want to create an inequality of weights that fit in this category. So if she's 68 kilograms, what is the smallest weight she could be that would round up to 68 kilograms? Well, if I had 67.5 kilograms, that would round up to 68 kilograms. What would be the heaviest weight she could be that would round down to 68 kilograms? Well, not including, it could go all the way up to 68.5. Not including 68.5 because that would then round up. So her upper and lower bounds would be 68.5 kilograms would be the upper bound not included, and then 67.5 kilograms included would be her lower bounds. So try numbers 2 and 3, a height measured to 155 centimeters, and you have a length and width of a rectangular garden plot. Find the upper and lower bounds of the perimeter. So go ahead and pause the video and try numbers 2 and 3. So first off, I went back and I added units. It's always more accurate to make sure we have units in here because 67.5 kilograms is very different than 67.5 pounds. So for number 2, it's very similar. If it's rounding to the nearest centimeter and it's 155 centimeters, then the interval, the smallest that it could have been would have been 154.5 centimeters included. The biggest it could have been would be 155.5 centimeters not included. So that would be the interval of her exact height. Okay. If you haven't already done so, go ahead and pause the video and find the upper and lower bounds of the perimeter of this garden. The perimeter of a rectangle is twice the length plus twice the width. So if the length is 172 meters to the nearest meter, that means it has to be somewhere between 171.5 and 172.5. Similarly, if the width is 64 meters to the nearest meter, then 63.5 up to 64.5 would be the intervals for the length and the width. So then I found the smallest possible length, which would be our perimeter, which would be assuming the smallest possible length and the smallest possible width. And I found that to be 470 meters. And then I did the same thing for the largest possible perimeter, which would be assuming that it's the largest possible in the interval for the length and the width, and got 474 meters. So the perimeter to the nearest meter is somewhere between 470 meters included and 474 meters not included. So again, whenever you're rounding to the nearest unit, there is this upper and lower bound of accuracy. Same thing if, even if you're measuring to the nearest half unit, there's an upper and lower bound of nearest accuracy. So one way that we measure our accuracy of our measurement is by our measurement error. So the measurement error is the difference between your exact value, which we represent with a V sub E, and your approximate value, which is your V sub A. So your measurement error is the difference between the two of them, or subtraction. So V sub A, your approximate, minus V sub E. This just tells you how far off you are, but it doesn't give you a real scale or a magnitude of how far off you are. So we take that and we calculate our percentage error, which gives us the percentage off that we are, because that depends on the scale that you're measuring on. So we take this measurement error and we divide it by our exact value, and then we take the absolute value of this. The reason we take the absolute value is we don't care if the approximate's smaller or bigger, we just want to know how far away it is, and that's what absolute value measures. And then we multiply this by 100% in order to make it a percentage. So you're calculating your percentage error, how far off your approximate or your measured value is, based on the exact value. Okay. One way that you can ruin accuracy is by rounding too much. So make sure you don't round in the middle, like of a multi-step calculation down here, rounding intermediate results. That will reduce your accuracy. So wait until the very end to round your final answer, and that will help with accuracy. So some examples of this: the fraction 22/7 is often used as an approximation of the constant pi. So first we want to look at how close, or to how many decimal places, 22/7 approximates pi. So go ahead and plug 22/7 into your calculator and plug pi into your calculator and see how close they are. So if you plug in 22/7 into your calculator, you get 3.142857143. If you plug pi into your calculator, you get 3.141592654. I wrote them to 4 decimal places here. And so you can see it's only to the first 2 decimal places, that 3.14 that pi is famous for. That's as far as 22/7 approximates pi. So 2 decimal places. So I want you to use the percentage error formula from the previous slide and calculate the percentage error of pi and 22/7. So your approximate value, so VA, is 22/7, and your exact value is pi. Make sure you don't use decimal already rounded. Actually use 22/7 and pi. So go ahead and set that up and find the percentage error. So I set up our percentage error here, so our approximate value minus our exact value divided by our exact value, so 22 divided by 7 minus pi, all divided by pi, and then I took that and I multiplied it by 100% in order to make it a percentage. So first, again, I wrote out longer than what I'm going to round to, a more exact value, and then this is IB. They tell me to round to 3 significant figures, so to 3 significant figures it would be 0.0402%. So pretty small, I mean 4 1,000ths of a percent, so 22/7 is a pretty good approximation of pi. For the next example, we want to calculate the density of a cube of sugar that weighs 2.45 grams, and one side of the cube is 1.2 centimeters. Cubes, all the sides are the same. And we want to measure this to 1 decimal place. So just a hint, density is weight divided by volume. So go ahead and calculate the density of this to 1 decimal place. So density is weight divided by volume. So first I had to calculate the volume of the cube. Volume of a cube is just cube the 3 sides, so you end up with 1.7 cubed, which is 1.728 centimeters cubed. So then density would be the weight, which was 2.45 grams, divided by the volume, which was 1.728 centimeters cubed. Plug that in our calculator, 1.41782, so on, and then it wants us to round to 1 decimal place. So then round this to 1 decimal place. I'm looking at the 4, and the 1's going to round it down, so 1.4 grams per centimeters cubed. Make sure when you're calculating something like this, you avoid premature rounding. So for example, I did not round the 1.728 or the 2.45. The answer button in your calculator is very useful, or scrolling up and grabbing it and pulling it down, so that you don't use a rounded answer. Section 1.4 is speaking scientifically, which we're going to be talking about scientific notation and exponents. So here's some vocab. Numerical expressions is something that only contains numbers and symbols of operations, versus algebraic expressions can contain variables in addition to the numbers and the symbols of operation. Exponentiation is the operation that we write as a to the nth power, where a is our base and n is our exponent or our power. If the exponent's a positive number, it determines how many times the base is being multiplied by itself. If the exponent is a negative number, it determines how many times 1 is being divided by the base. Here are laws of exponents. I would pause the video and write them down. We have laws, and then we have examples over here. So the first one, x to the nth power, that means x times x times x times itself n times. So for example, 3 to the fourth is 3 times 3 times 3 times 3, which is 81. Anything to the first power is just itself, so 6 to the first is equal to 6. Anything to the 0 power is equal to 1, so 7 to the 0, x to the 0, anything is equal to 1. If you multiply two things with the same base, you can add the exponents. So if you have x squared times x cubed, that's the same thing as x to the 2 plus 3, or x to the 5th. If you divide two things with the same base, you can subtract the exponents, the numerator minus the denominator. So x to the 6th divided by x squared would be x to the 6 minus 2, which is x to the 4th. When you raise a power to a power, you multiply them. So x squared to the 3rd power would be x to the 2 times 3, which is x to the 6th. If you multiply or divide two things and raise that whole thing to a power, you can distribute. Only multiplication and division. So x times y cubed is x cubed y cubed, x divided by y squared is x squared divided by y squared, and then a negative exponent flips it over. So if the negative's in the numerator, it now becomes in the denominator. It can also go the other way. So x to the negative 3 is the same thing as 1 over x cubed. And remember, you can always go both directions. You could write this as a negative exponent or a negative exponent as a reciprocal. So here are some examples. For the first one, we want to use our laws of exponents and possibly your graphing calculator. That's what GDC stands for, graphic display calculator, to write the following as a power of just a single number. And then the bottom one, you're writing it as a single power of x. So go ahead and pause the video, use your exponent laws to simplify these. So for the first one, you have 2 divided by 2 cubed plus 2 squared quantity cubed. So for the first one, this has an invisible power of 1 in the numerator here, so I used the raising two bases, dividing two things with the same base, subtract the exponent, so 2 to the 1 minus 3, and then raise a power to the power, you multiply them, so 2 to the 2 times 3. So you have 2 to the negative 2 plus 2 to the 6th, which is 1 over 2 squared plus 2 to the 6th. So 1/4 plus 64, which is 64.25. For B, I did the numerator first because of our order of operations. There's kind of an invisible parentheses here. So 4, and then I'm multiplying two things with the same base, so I add the exponents, 3 plus a negative 7, so 3 minus 7. I get 4 to the negative 4, divided by 4 squared. I'm dividing two things with the same base, so I subtract the exponents. 4 to the negative 4 minus 2 is 4 to the negative 6th, which is 1 over 4 to the 6th, which is 1 over 4,096. So if you haven't already done so, go ahead and pause the video and do number 2. So for the first one, you're raising a power to a power, multiply them, so you end up with x to the 2 times 3, which is x to the 6th. For the second one, you're dividing two things inside a parenthesis, raising to a power, so you distribute the 4th power to both the numerator and the denominator. So 1 to the 4th divided by x squared quantity to the 4th power. You end up with 1 over x to the 8th, or x to the negative 8. Raising a power to a power, again, multiply them. You get x to the negative 3, or 1 over x cubed, depending on which way you want to write it. And then D, I did the numerator first. I added the exponents because you're multiplying. 3 plus a negative 1, so x squared over x to the 5th. And then I subtracted the numerator minus denominator exponent. You get x to the negative 3, or 1 over x cubed. So again, this has been using the laws of exponents to simplify these, along with the order of operations. The last part of this is standard form or scientific notation, so numbers written of the form a times 10 to the nth power, where a we call our coefficient or our mantissa, and a is always between 1 included and 10 not included. So basically there's no tens place, it's always a decimal, like 9.5, something like that. And then n is always going to be an integer. So for example, if I wanted to write the number 317.4 in scientific notation. I've always used just the first digit. That's going to be the only thing that's on this side of the decimal place, and then everything else is on the other side of the decimal place. So it'd be 3.174, and then it's times 10, and then how far did we move it over? We moved the decimal place over 2 places, and we're making it bigger, so we want it to be a positive 2. So it's 3.174 times 10 to the second power, because if you write this not in scientific notation or not in standard form, you'd be making this bigger. Versus if you wanted something like 0.03174 and we wanted to write this in scientific notation, same thing. You find the first non-zero digit, which in this case would be the 3. Everything after that would be a decimal. And then how far did we move the decimal over? Well, we moved it 2 places to the right, so it's going to be times 10 to the negative 2, because we are making it smaller when we take it out of scientific notation or standard form. So positive exponent if you're making it bigger out of scientific notation, negative exponent if when you take it out of scientific notation it gets smaller. Okay. So find the volume of a computer chip, which is going to be a cuboid. That is 2.44 times 10 to the negative 6 meters wide. So that means 2.44, and then move this decimal place to the left 6 places. And then 1.5 times 10 to the negative 7 meters long, and 2.15 times 10 to the negative 4 meters high. And we want to write our final answer in the standard form. So go ahead and pause the video and try this. So volume of a cuboid is just length times width times height. So 2.44 times 10 to the negative 6 meters times 1.5 times 10 to the negative 7 meters times 2.15 times 10 to the negative 4 meters. Since this is all multiplication, you can actually rewrite this using the commutative property. So I took the 2.4 for the 1.5 and the 2.15, and I multiplied those by each other first, and then I did the 10 to the negative 6 times 10 to the negative 7 times 10 to the negative 4 second. So 2.44 times 1.5 times 2.15 is 7.869. And then using the laws of exponents, I just added all these exponents together and got times 10 to the negative 17. So this is the volume of this computer chip is 7.869 times 10 to the negative 17 meters cubed. You can also use your graphing calculator. Your graphing calculator does scientific notation, and will do this multiplication for you as well. So this has been scientific notation as well as rounding and accuracy.